familiar with microwave ovens. The component inside this machine that's responsible for producing microwaves is known as a magnetron. When high voltage is applied to the cathode of a magnetron, it ejects many electrons through thermionic emission. Let's observe the behavior of one electron and its resulting impact on the cavity. When the electron comes towards the anode, it repels the nearest cavity's electrons. Due to this electron displacement, positive charges form on that surface. The displaced electrons will obviously make a surface of negative charges on the nearby cavity. To simplify the animation, we'll represent these surface charges with a line of charges. Now, something peculiar happens. The same charge pattern is automatically induced in all the cavities. Later, these distributed charges go for LC oscillation and eventually produce microwaves. Do you know how charges induced in just one cavity lead to induction of charges in the other cavities? In order to find the answer to this question, let's consider a metal bar. Assume an external electric field is applied to it. This electric field disturbs the free electrons in the metal and develops charges on the surfaces at both ends. These newly formed charged surfaces will generate another electric field. The electron displacement will happen until the newly formed electric field exactly cancels the external electric field, which is a fundamental property of metal. Metal will always rearrange its electrons and make sure that its net electric field is zero. Now, let's examine a slightly different case, a metal bar with many cavities. Assume the electrons from one cavity's surface are displaced to the next surface due to some external force. As a result, an electric field will be present inside this cavity. What about the metal region outside this cavity? You can see the electric field in this region is getting cancelled perfectly. Zero electric field in the metal region means this is a stable system, and introduction of the charges in the first cavity will not have any effect on the remaining cavities. Now, let's bend this structure into a cylinder. What do you think will happen? Interestingly, the behavior of the cylindrical case is quite different from the linear case. Let's see why. The main difference here is that the resultant electric field produced by the negative and positive charges in a metal spike does not equal zero, due to the fact that the electric field lines produced by this new curved geometry are not exactly opposite. They are at an angle. This angle means that the simple positive and negative charge case is not a stable arrangement. As we learned in the beginning, the electric field inside any metal should be zero. This condition is possible only with a charge distribution, as shown. Here, using vector addition, we can prove that all the electric field lines are getting cancelled inside the metal body. Let's analyze the concept we just learned using finite element analysis. Here, we use the FEA software EMWorks to predict the electric field inside the metal part. In this case, surface charges are given according to the charge distribution we predicted in the previous session. You can see that throughout the metal body, the electric field value is almost zero, whereas in the cavity region, a good amount of electric field is present. It's so interesting to see how fundamental physics plays a crucial role in the workings of such an important device. Thank you for watching the video, and don't forget to be a part of our team.